The story of human fascination with the stars is as old as civilization itself. From ancient times, people have looked up at the night sky in wonder, crafting myths, mapping the stars, and trying to make sense of the vastness of the universe. For millennia, our ancestors believed that Earth was the center of it all, a fixed point around which the sun, moon, stars, and planets revolved in perfect harmony. This belief, known as the geocentric model of the universe, dominated human thought for over 1,000 years, reinforced by the teachings of Aristotle and later cemented by Ptolemy in the 2nd century AD. But in the early 17th century, the foundations of this ancient view of the cosmos began to crumble, thanks to the work of a revolutionary thinker. His name was Galileo Galilei, and his observations and theories would change humanity's understanding of the universe forever. Galileo's contributions to science and astronomy went far beyond a single breakthrough. He was a man of many talents, a mathematician, physicist, engineer, and inventor. But it was his work as an astronomer that left the most profound impact on the world. Using the newly invented telescope, Galileo was able to observe the heavens in a way that no human had ever done before. What he saw through his telescope shocked the scholarly and religious establishments of his time. Galileo's observations provided direct evidence that contradicted the established views of the universe, and his unwavering commitment to truth in the face of opposition marked the beginning of the scientific revolution. In 1609, Galileo heard of a new invention from the Netherlands, the telescope. Initially designed for military purposes, the telescope allowed viewers to see distant objects more clearly. Galileo, always eager to experiment, constructed his own version of the device. He painstakingly ground lenses and perfected the design, eventually creating a telescope that could magnify objects up to 20 times. Armed with this new instrument, Galileo turned his gaze to the stars and planets, making discoveries that would shake the very core of astronomical knowledge. The first of these discoveries came in January 1610, when Galileo trained his telescope on the planet Jupiter. To his amazement, he noticed 4 small stars that seemed to hover near the planet. Night after night, he observed these points of light, realizing that they were not fixed stars at all, but moons orbiting Jupiter. This was a groundbreaking discovery. It provided the first clear evidence that not everything in the cosmos revolved around the Earth. These 4 moons, now known as the Galilean moons, Io, Europa, Ganymede, and Callisto, showed that there were other centers of motion in the universe, directly contradicting the geocentric model that had been accepted for centuries. Galileo's observations did not stop there. As he continued to peer through his telescope, he discovered that the planet Venus went through phases similar to those of the Moon, proving that Venus must orbit the Sun, not the Earth. This discovery provided further evidence for the heliocentric theory proposed by Nicolaus Copernicus decades earlier. Galileo also observed that the surface of the Moon was not smooth, as previously believed, but covered with mountains and craters. This shattered the Aristotelian idea that celestial bodies were perfect, unblemished spheres. These discoveries were revolutionary, but they did not come without a cost. Galileo's findings challenged the deeply held beliefs of the Catholic Church, which adhered to the Ptolemaic model of the universe. The idea that the Earth was not the center of the universe was seen as a threat to religious doctrine, and Galileo soon found himself in conflict with the Church. In 1616, the Catholic Church officially condemned the heliocentric model, and Galileo was warned not to defend it. Despite this warning, Galileo continued his work. In 1632, he published his Dialogue concerning the two chief world systems, in which he compared the Ptolemaic and Copernican models. The book was written in the form of a conversation between three characters: one who supported the geocentric model, one who supported the heliocentric model, and one neutral observer. Though Galileo presented the arguments for both sides, it was clear that he favored the Copernican view. This work sparked a fierce reaction from the Church, and in 1633, Galileo was summoned to Rome to face the Roman Inquisition. Under intense pressure, Galileo was forced to recant his support for the heliocentric model. He spent the last years of his life under house arrest, forbidden from teaching or writing about his discoveries. Yet, even in confinement, Galileo's mind remained active. He continued to write about physics and mechanics, laying the groundwork for future generations of scientists, including Isaac Newton. Though he was silenced by the Church, Galileo's ideas could not be suppressed. His work spread across Europe, inspiring a new wave of scientific inquiry. The story of Galileo is one of courage, curiosity, and a relentless pursuit of truth. He lived at a time when challenging established beliefs came with great personal risk, yet he did so fearlessly, driven by a deep desire to understand the universe. His discoveries not only revolutionized astronomy, but also helped to establish the scientific method, a systematic approach to investigation based on observation, experimentation, and evidence. Galileo's legacy is vast, and his contributions to science are still felt today. His telescopic observations paved the way for modern astronomy, and his work in physics laid the foundations for classical mechanics. But perhaps his greatest gift to humanity was his willingness to question the status quo, and to seek answers through observation and reason. In doing so, he helped to ignite the flame of the scientific revolution, a movement that would forever change the way we view the world and our place in the cosmos. As you begin this journey through the life and discoveries of Galileo, imagine the night sky as he saw it. A vast, mysterious expanse filled with stars, planets, and endless possibilities. Galileo's story is not just one of scientific breakthroughs, but of a man who dared to challenge the world's understanding of the universe, opening the door to a new era of discovery. Chapter 1. The Early Life of Galileo Galilei. Galileo Galilei was born on February 15, 1564, in the city of Pisa, Italy, a region that was part of the Duchy of Florence at the time. His family belonged to the lower ranks of the nobility, though they were not wealthy. Galileo's father, Vincenzo Galilei, was a man of many talents. A gifted musician and music theorist, Vincenzo was known for his critical approach to traditional views on music theory. He believed that music, like other disciplines, should be grounded in scientific principles rather than simply following long-established traditions. From his father, young Galileo inherited not only a passion for the arts, but also a skeptical mindset that would serve him well in his future endeavors. Galileo's early education was shaped by his father's influence and by the intellectual environment of the Italian Renaissance, a period marked by a revival of learning based on classical knowledge. As a boy, he showed a natural aptitude for learning and was particularly interested in mathematics. However, his formal education began with a focus on grammar, logic, and classical literature, as was customary for young men of his status. At the age of 10, Galileo and his family moved from Pisa to Florence, where his father sought better opportunities. While in Florence, Galileo was sent to the Camaldolese monastery at Vallombrosa, nestled in the hills just outside the city. The monastery, known for its rigorous academic curriculum, introduced Galileo to a more structured education. Here, he was exposed to the study of theology, philosophy, and Aristotelian science. Though he enjoyed his studies, it was mathematics that captured his imagination. The elegant logic of mathematics appealed to his inquisitive mind, and he quickly became proficient in the subject. Despite his growing interest in mathematics, Galileo's father had different plans for him. In 1581, at the age of 17, Galileo was sent back to Pisa to study medicine at the University of Pisa. His father hoped that a medical career would provide financial security for the family, but Galileo found little joy in the study of medicine. Though he respected his father's wishes, he could not shake his fascination with mathematics and natural philosophy. It was during his time at the University of Pisa that Galileo experienced an event that would forever change the course of his life. While attending a service at the Cathedral of Pisa, he noticed a large chandelier swinging gently back and forth. As he observed the chandelier, Galileo realized something remarkable. The time it took for the chandelier to complete a full swing remained constant, regardless of the amplitude of the swing. This discovery, though seemingly simple, would later lead to his groundbreaking work on the laws of motion and the development of the pendulum as a timekeeping device. Despite his growing interest in physics and mathematics, Galileo did not abandon his medical studies immediately. However, he increasingly sought out opportunities to study mathematics on the side, attending lectures by local mathematicians and immersing himself in the works of Euclid and Archimedes. It was Archimedes, in particular, who would have a lasting influence on Galileo's thinking. Archimedes' approach to mathematics as a tool for understanding the physical world resonated deeply with Galileo, and he began to see mathematics as the key to unlocking the secrets of nature. In 1585, after 4 years of study, Galileo left the University of Pisa without a degree. His departure was prompted not by failure, but by a growing conviction that his true calling lay in the study of mathematics and natural philosophy. With the support of his father, who eventually accepted Galileo's passion for these subjects, he returned to Florence and began working as a private tutor in mathematics. This period of tutoring allowed Galileo to hone his skills and deepen his understanding of the mathematical principles that would later form the basis of his revolutionary discoveries. In 1589, Galileo secured a position as a professor of mathematics at the University of Pisa. This appointment marked the beginning of his academic career and gave him the freedom to pursue his research into the laws of motion. During this time, Galileo began conducting experiments that would challenge the traditional Aristotelian view of physics, which had dominated European thought for centuries. According to Aristotle, heavier objects fell faster than lighter ones, a belief that had gone unquestioned for nearly 2 millennia. Galileo, however, was skeptical of this idea. He believed that all objects, regardless of their mass, should fall at the same rate, and he set out to prove it through experimentation. According to popular legend, Galileo demonstrated this by dropping 2 spheres of different masses from the Leaning Tower of Pisa. both spheres, as Galileo predicted, reached the ground at the same time, providing clear evidence that Aristotle's theory was incorrect. Though the story of the Leaning Tower experiment may be apocryphal, it symbolizes Galileo's method of challenging established beliefs through empirical observation and experimentation. While at the University of Pisa, Galileo also explored the concept of inertia. He proposed that an object in motion would continue moving indefinitely unless acted upon by an external force, a radical departure from the Aristotelian view that objects naturally came to rest. This principle of inertia would later form the foundation of Newton's first law of motion, but it was Galileo who first formulated the idea. Despite his groundbreaking work, Galileo's time at the University of Pisa was not without challenges. His rejection of Aristotelian physics earned him the disapproval of many of his colleagues, who viewed his ideas as heretical and dangerous. In 1592, after 3 years at Pisa, Galileo accepted a more prestigious position as the chair of mathematics at the University of Padua, one of the most renowned universities in Europe at the time. The move to Padua marked the beginning of a new and productive phase in Galileo's life. Here, he enjoyed greater intellectual freedom and found himself surrounded by like-minded scholars. It was in Padua that Galileo would conduct some of his most important research, including his early experiments with telescopes and his discoveries about the nature of the cosmos. Though Galileo is best known for his work in astronomy, his contributions to the study of motion and mechanics were equally significant. His experiments in Pisa and Padua laid the groundwork for modern physics, and his insistence on empirical observation and mathematical reasoning helped to usher in a new era of scientific inquiry. Galileo's work would eventually challenge the very foundations of medieval thought, leading to a conflict with the Church that would define his later years. Galileo's early life was marked by a constant search for truth, a search that would lead him to question long-held beliefs and to push the boundaries of human understanding. As he gazed up at the night sky, he saw not just stars and planets, but a universe waiting to be explored, a universe far more complex and beautiful than anyone had ever imagined. Chapter 2. The Invention of the Telescope and Galileo's Astronomical Discoveries. By the early 17th century, Galileo Galilei had already established himself as one of Europe's most accomplished mathematicians and physicists. His work at the University of Padua had earned him a reputation for challenging conventional wisdom, particularly in the fields of motion and mechanics. However, it was his contributions to astronomy, fueled by his groundbreaking use of a new instrument, that would make him a central figure in the scientific revolution. In 1608, a Dutch eyeglass maker named Hans Lippershey is credited with inventing the first telescope, a device that used lenses to magnify distant objects. Although Lippershey's invention was rudimentary, word of the new device quickly spread across Europe. By 1609, news of the telescope had reached Galileo in Italy, and he immediately recognized its potential for scientific observation. Though Galileo did not invent the telescope, he was among the first to grasp its revolutionary implications, and he wasted no time in creating his own, more powerful version of the instrument. Galileo began by experimenting with different combinations of lenses, grinding them himself to achieve the clearest possible magnification. His efforts paid off, and by the summer of 1609 he had constructed a telescope capable of magnifying objects up to 20 times their original size, a significant improvement over the early Dutch models. With this new tool in hand, Galileo turned his attention to the heavens, and what he saw would forever alter humanity's understanding of the universe. In the fall of 1609, Galileo pointed his telescope toward the moon, an object that had been studied by astronomers for centuries. However, through his telescope, Galileo saw something no one had seen before. The moon's surface was not smooth and perfect as Aristotle and other philosophers had believed. Instead, it was rough and uneven, covered with mountains, valleys, and craters. This discovery shattered the long-held Aristotelian view that celestial bodies were flawless and unchanging, and it provided the first real evidence that the moon was a world much like Earth. Galileo carefully recorded his observations of the moon's surface, creating detailed drawings that showed the light and shadow across its mountains and craters. His findings challenged the prevailing belief that the heavens were fundamentally different from the Earth, and they suggested that the same natural forces that shaped our planet might also be at work in the rest of the cosmos. But Galileo's observations did not stop there. In January 1610, he turned his telescope toward the planet Jupiter, one of the brightest objects in the night sky. As he observed the planet night after night, he noticed 4 small points of light near Jupiter, which appeared to move around the planet. At first, Galileo thought these were stars, but after careful observation, he realized that they were, in fact, moons orbiting Jupiter. He had discovered what are now known as the Galilean moons, Io, Europa, Ganymede, and Callisto. This discovery was groundbreaking for several reasons. First, it provided concrete evidence that not everything in the universe revolved around the Earth, as the geocentric model proposed. The existence of moons orbiting Jupiter showed that other celestial bodies could serve as centers of motion, directly contradicting the Ptolemaic system that had been accepted for centuries. Second, Galileo's discovery of these moons demonstrated the power of observation and empirical evidence in challenging long-held beliefs. Galileo quickly published his findings in a short treatise titled Sidereus Nuncius, the Starry Messenger, in March 1610. The book caused an immediate sensation across Europe, drawing both admiration and controversy. In it, Galileo detailed his observations of the moon, Jupiter's moons, and other celestial phenomena, and he presented his findings as a challenge to the traditional understanding of the cosmos. His reputation as a brilliant scientist and observer grew rapidly, but so did the opposition from those who felt threatened by his discoveries. One of Galileo's most significant contributions to astronomy came later in 1610, when he observed the planet Venus. As he trained his telescope on Venus, Galileo noticed that the planet went through phases similar to the phases of the moon. These phases indicated that Venus orbited the Sun, not the Earth, providing further support for the heliocentric theory proposed by Nicolaus Copernicus in 1543. The heliocentric model, which placed the Sun at the center of the solar system, directly contradicted the geocentric model, which held that the Earth was the center of the universe. Galileo's observation of Venus was perhaps the most definitive evidence in favor of the Copernican system. If Venus orbited the Sun, it meant that Earth was not the center of all celestial motion. a revolutionary idea that fundamentally altered humanity's understanding of its place in the cosmos. The phases of Venus provided observational proof of the heliocentric theory, and Galileo's work played a crucial role in advancing this new model of the universe. In addition to his observations of the Moon, Jupiter's moons, and Venus, Galileo made several other important discoveries during this period. He observed the rings of Saturn. Although his telescope was not powerful enough to discern their true nature, and he discovered that the Milky Way was composed of countless individual stars, previously invisible to the naked eye. These discoveries further demonstrated the power of the telescope and the importance of empirical observation in understanding the universe. However, Galileo's findings also brought him into direct conflict with the Catholic Church. The heliocentric model, which Galileo supported, contradicted the Church's teachings, which were based on the Ptolemaic system. In 1616, the Church declared the heliocentric model to be heretical and forbade Galileo from publicly advocating for it. Despite this, Galileo continued his research in private, determined to uncover the truth about the cosmos. In 1623, Galileo's fortunes seemed to improve when his longtime friend and supporter, Cardinal Maffeo Barberini, was elected pope and took the name Urban VIII. Encouraged by this change in leadership, Galileo felt emboldened to write a new book, Dialogue Concerning the Two Chief World Systems, which compared the geocentric and heliocentric models. Though Galileo attempted to present both models in a balanced way, it was clear that he favored the heliocentric view. Dialogue Concerning the Two Chief World Systems was published in 1632, and it quickly reignited the controversy over the structure of the universe. The Church, feeling that Galileo had defied its earlier orders, summoned him to Rome to stand trial before the Roman Inquisition. In 1633, under the threat of torture, Galileo was forced to recant his support for the heliocentric model, and he spent the rest of his life under house arrest. Despite this, his ideas continued to spread across Europe, inspiring future generations of scientists and astronomers. Galileo's use of the telescope revolutionized the study of astronomy and challenged the very foundations of medieval thought. His discoveries not only provided evidence for the heliocentric model, but also demonstrated the importance of observation, experimentation, and critical thinking in the pursuit of knowledge. Galileo's work laid the foundation for modern astronomy, and his commitment to scientific inquiry, even in the face of opposition, helped to usher in a new era of discovery. Chapter 3. Galileo's Conflict with the Church and the Trial. By the time Galileo Galilei published his Siderius Nuncius in 1610, his name had spread throughout Europe as one of the foremost minds of his generation. His discoveries with the telescope, especially his observations of Jupiter's moons, the phases of Venus, and the rough surface of the Moon, had shaken the foundations of established astronomy. Galileo was no longer just a mathematician and physicist. He had become the face of a new way of thinking, one that relied on observation and evidence rather than long-standing doctrine. However, the revolutionary nature of Galileo's discoveries also brought him into direct conflict with the Catholic Church. For centuries, the Church had adhered to the geocentric model of the universe, based on the teachings of Aristotle and Ptolemy. This model placed the Earth at the center of the cosmos, with all other celestial bodies, including the sun and stars, revolving around it. The geocentric model was not just a scientific theory. It had become deeply intertwined with theological teachings, symbolizing humanity's central place in God's creation. The heliocentric theory, proposed by Nicolaus Copernicus in 1543, challenged this worldview by suggesting that the Earth and other planets orbited the Sun. Copernicus's theory, though mathematically elegant, had not been widely accepted during his lifetime, as it lacked solid observational proof. However, Galileo's telescopic observations provided exactly that. His discovery that Venus went through phases similar to those of the Moon offered clear evidence that Venus orbited the Sun, not the Earth, supporting the heliocentric model. The implications of Galileo's work went beyond science. By challenging the geocentric model, Galileo was indirectly challenging the authority of the Church, which had long upheld the Earth-centered universe as a reflection of divine order. As Galileo's findings gained prominence, so did the opposition from those who saw his work as a threat to religious teachings. The tension between Galileo's scientific discoveries and the Church's doctrines set the stage for one of the most famous trials in the history of science. The Church's response and the 1616 condemnation. In 1616, the Catholic Church took its first significant action against Galileo and the heliocentric model. A committee of theologians, known as the Roman Inquisition, was convened to examine the compatibility of the heliocentric theory with Scripture. The Inquisition concluded that the idea of a sun-centered universe was formally heretical, because it contradicted certain passages in the Bible that appeared to support the geocentric model. As a result, the Church officially condemned the heliocentric theory. Galileo was not yet directly implicated, but the Church took steps to prevent the spread of Copernican ideas. Nicolaus Copernicus's book De Revolutionibus Orbium Coelestium, which had introduced the heliocentric model, was placed on the Church's index of forbidden books. The Church also warned Galileo not to publicly defend or advocate for the heliocentric theory, though he was allowed to discuss it hypothetically as a mathematical model. Although the condemnation of 1616 forced Galileo to remain cautious, he continued his research in private. He maintained correspondence with other scientists across Europe, sharing his observations and ideas, and he began to look for ways to reintroduce the heliocentric theory into public discourse without directly defying the Church. His cautious approach allowed him to avoid immediate conflict, but it did not quell his desire to pursue the truth. Galileo's dialogue and the return to controversy. In 1623, Galileo's fortunes seemed to take a turn for the better when a longtime friend and supporter, Cardinal Maffeo Barberini, was elected pope and took the name Urban VIII. Barberini had previously admired Galileo's work and had expressed a relatively open-minded view on the debate between the geocentric and heliocentric models. Encouraged by the election of a more sympathetic pope, Galileo saw an opportunity to revisit the subject of the universe's structure. In 1624, Galileo began work on a new book, one that would compare the two prevailing models of the cosmos, the Ptolemaic, geocentric system, and the Copernican, heliocentric system. Galileo titled the book Dialogue Concerning the Two Chief World Systems, and it was structured as a conversation between three characters: Salviati, who represents the Copernican view, Simplicio, who defends the Ptolemaic system, and Sagredo, an intelligent but neutral observer. Galileo intended the dialogue to be an objective comparison of the two models, but it was clear to readers that the arguments in favor of the heliocentric model were stronger. Salviati, the character who advocates for the Copernican theory, is portrayed as knowledgeable and logical, while Simplicio, the defender of the geocentric model, comes across as somewhat simplistic and stubborn. Though Galileo claimed that the dialogue was written to explore both models without directly supporting one over the other, the text was seen by many as a defense of heliocentrism. The dialogue was completed in 1632 and was soon published with formal approval from the Church's censors. Initially, the book was well received, and it reignited public interest in the debate over the structure of the universe. However, it did not take long for the Church to realize the implications of Galileo's work. Pope Urban VIII, who had once been Galileo's ally, felt personally betrayed by the book. He believed that the character of Simplicio was a thinly veiled caricature of himself, and he took offense at Galileo's portrayal of the geocentric model as outdated and illogical. The Trial of 1633. In response to the growing controversy, the Church took swift action. In 1633, Galileo was summoned to Rome to stand trial before the Roman Inquisition on charges of heresy. The trial focused on whether Galileo had violated the Church's 1616 decree, which had forbidden him from defending the heliocentric model as a reality. Despite his protests that he had only presented the Copernican system as a hypothetical theory, the Inquisition found him guilty of vehement suspicion of heresy. Under the threat of torture, Galileo was forced to recant his support for the heliocentric model. In a formal abjuration, Galileo publicly renounced the idea that the Earth moved around the Sun, declaring that he had erred in his defense of Copernicanism. According to legend, after recanting, Galileo muttered under his breath the famous words, "E pur si muove," and yet it moves, though this story is likely apocryphal. As punishment, Galileo was sentenced to house arrest for the remainder of his life. He spent the next 9 years confined to his villa in Arcetri, near Florence, where he continued to write and conduct scientific research, though his movements and communications were strictly limited. Despite his formal recantation, Galileo never abandoned his belief in the heliocentric model, and his final years were spent working on a new book that would summarize his contributions to physics and motion. The Aftermath, and Galileo's Legacy. Galileo died in 1642 at the age of 77, still under house arrest. His trial and condemnation marked the end of a public career that had challenged the very foundations of medieval science and thought. However, his ideas could not be silenced. Despite the Church's efforts to suppress his work, Galileo's discoveries continued to spread across Europe, influencing the next generation of scientists, including Johannes Kepler and Isaac Newton. It would take centuries for the Church to fully acknowledge Galileo's contributions to science. In 1758, the Catholic Church lifted the ban on books advocating heliocentrism, and in 1835, Galileo's works were finally removed from the Index of Forbidden Books. In 1992, more than 350 years after his trial, Pope John Paul II formally acknowledged the Church's error in condemning Galileo, recognizing his role as a pioneer of modern science. Galileo's trial is often seen as a symbol of the conflict between science and religion, but it also represents the triumph of observation and evidence over dogma. Galileo's commitment to the pursuit of truth, even in the face of overwhelming opposition, helped to lay the foundations for the scientific revolution. His discoveries in astronomy and physics transformed humanity's understanding of the cosmos, and his insistence on empirical observation became a cornerstone of the scientific method. Galileo's legacy lives on not only in the telescopes and observatories that bear his name, but in the spirit of curiosity and inquiry that continues to drive scientific discovery. His life was a testament to the power of questioning established beliefs and to the importance of seeking knowledge, even when it challenges the status quo. Chapter 4. Galileo's Contributions to Physics and the Laws of Motion. While Galileo Galilei is best known for his revolutionary astronomical discoveries, his contributions to the field of physics were equally significant. Long before he became embroiled in the controversy over the structure of the universe, Galileo was focused on understanding the fundamental principles that governed motion. His work in mechanics laid the foundation for what would later become classical physics, and his pioneering experiments challenged the long-standing views of Aristotle, which had dominated European thought for centuries. In the late 16th and early 17th centuries, the Aristotelian view of motion held that heavier objects fall faster than lighter ones, and that an external force was required to keep an object in motion. According to this view, an object's natural state was to remain at rest unless acted upon by a force, and once that force was removed, the object would come to a stop. These ideas had been accepted for nearly 2 millennia, and they formed the basis of medieval physics. Galileo, however, was skeptical of this traditional understanding of motion. From his earliest days as a student, he had questioned Aristotle's conclusions, and he sought to test them through experimentation. Rather than relying on abstract reasoning, as many of his contemporaries did, Galileo believed that the truth about nature could only be discovered through careful observation and empirical testing. The Leaning Tower of Pisa experiment. Separating myth from fact. One of the most famous stories about Galileo's early experiments comes from his time at the University of Pisa. According to legend, Galileo climbed the Leaning Tower of Pisa and dropped 2 spheres of different masses to demonstrate that they would hit the ground at the same time. This experiment was said to have disproved Aristotle's theory that heavier objects fall faster than lighter ones. Though the story of the Leaning Tower of Pisa experiment is widely circulated, there is little historical evidence to confirm that it actually took place in this manner. Whether or not Galileo conducted this particular experiment, what is certain is that he did carry out numerous tests to investigate the nature of falling bodies. His work revealed that, contrary to Aristotle's teachings, all objects fall at the same rate in the absence of air resistance, regardless of their mass. This discovery was a radical departure from the accepted understanding of motion, and it laid the groundwork for the later development of Newton's laws of motion. Galileo's findings were based on an ingenious method of experimentation. Since it was difficult to measure the speed of falling objects with precision, Galileo devised a way to slow down the motion so that it could be observed more easily. He rolled balls down inclined planes, carefully measuring the distance they traveled and the time it took for them to reach various points. These experiments allowed him to study the acceleration of objects and to develop a mathematical description of uniformly accelerated motion. Galileo's law of falling bodies. Through his experiments with inclined planes, Galileo formulated what would later be known as the law of falling bodies. He discovered that the distance an object falls is proportional to the square of the time it has been falling. In other words, if an object falls for twice as long, it will cover 4 times the distance. This relationship between time and distance became one of the key principles of classical mechanics. Galileo's law of falling bodies marked a turning point in the study of motion. For the first time, the motion of objects could be described mathematically, providing a clear and testable explanation of how bodies fall under the influence of gravity. This was a major step toward the development of modern physics, and it represented a break from the Aristotelian tradition of qualitative reasoning about motion. Galileo's experiments also led him to a deeper understanding of the concept of acceleration. He recognized that objects falling under the influence of gravity do not move at a constant speed. Instead, they accelerate as they fall. This insight was crucial to the later development of the concept of gravitational acceleration, which would eventually become one of the cornerstones of Newtonian physics. The principle of inertia. One of Galileo's most important contributions to physics was his formulation of the principle of inertia. In contrast to the Aristotelian view that an external force was required to keep an object in motion, Galileo proposed that an object in motion would continue moving indefinitely, unless acted upon by an external force, such as friction or air resistance. This principle of inertia was revolutionary because it challenged the long-held belief that objects naturally came to rest. Galileo arrived at this conclusion through a series of thought experiments and practical observations. For example, he imagined a scenario in which a ball was placed on a perfectly smooth, frictionless surface. In such a situation, Galileo reasoned, the ball would continue moving at a constant speed forever, since there would be no external force to slow it down. This insight formed the basis of what would later become Newton's first law of motion, or the law of inertia. Galileo's principle of inertia fundamentally changed the way scientists thought about motion. It introduced the idea that objects have a natural tendency to maintain their current state of motion, whether at rest or in uniform motion, unless acted upon by an external force. This concept laid the groundwork for the development of classical mechanics and helped to explain the motion of objects in both terrestrial and celestial environments. Galileo's work on projectiles and parabolic motion. In addition to his studies of falling bodies and inertia, Galileo made significant contributions to the understanding of projectile motion. Prior to Galileo's work, it was commonly believed that projectiles followed a straight line for part of their trajectory and then dropped vertically to the ground. This belief was based on the Aristotelian idea that objects could not simultaneously have both horizontal and vertical motion. Galileo, however, demonstrated that projectiles actually follow a curved parabolic path. He showed that the motion of a projectile could be broken down into 2 components: horizontal motion, which remains constant, and vertical motion, which is influenced by gravity. The combination of these 2 motions creates a parabolic trajectory, with the projectile accelerating downward as it moves horizontally. This discovery was another major departure from Aristotelian physics, and it had important implications for the study of motion. Galileo's understanding of projectile motion allowed for the prediction of the path of any object moving through the air, whether it was a cannonball or a thrown stone. His work laid the foundation for later developments in the field of ballistics and had a profound impact on both physics and engineering. Galileo's legacy in physics. Galileo's contributions to the study of motion were transformative. His experiments and observations challenged the long-standing Aristotelian view of the natural world and replaced it with a new, mathematically based understanding of motion. By emphasizing the importance of experimentation and empirical evidence, Galileo helped to establish the scientific method as the primary tool for investigating the physical universe. His work on falling bodies, inertia, and projectile motion not only laid the groundwork for the later development of Newtonian physics, but also opened the door to a deeper understanding of the fundamental laws that govern the natural world. Galileo's insistence on testing theories through observation and experimentation represented a major shift in the approach to scientific inquiry, and it played a key role in the birth of modern science. Though Galileo's later years were marked by conflict with the Catholic Church over his support for the heliocentric model, his contributions to physics were widely recognized and celebrated in his lifetime. His ability to bridge the gap between mathematics and the physical world allowed him to make groundbreaking discoveries that would shape the future of science for centuries to come. Galileo's legacy in physics is not just one of discovery, but also of method. His approach to science, rooted in observation, experimentation, and the use of mathematics to describe natural phenomena, set the stage for the scientific revolution. Today, Galileo is remembered not only as the father of modern astronomy, but also as one of the founding figures of classical mechanics, a field that continues to underpin our understanding of the physical universe. Chapter 5. Galileo's Final Years and Lasting Legacy. After his trial in 1633, Galileo Galilei's life changed dramatically. Once a respected figure among scholars and scientists across Europe, Galileo now found himself condemned by the Catholic Church, confined to his villa near Florence under house arrest. His work in support of the heliocentric model of the universe had brought him into conflict with the highest religious authorities, and his forced recantation had been a humiliating conclusion to a lifetime of groundbreaking scientific inquiry. However, despite the Church's attempts to silence him, Galileo's mind remained as active as ever. Though his public life was effectively over, he continued to pursue his scientific interests, writing, studying, and conducting experiments until the very end of his life. These final years, though marked by physical limitations and isolation, were still a time of intellectual achievement for Galileo. His legacy, already immense during his lifetime, would only grow after his death, influencing the course of science for centuries to come. House arrest and continuing research. Following his trial, Galileo was initially confined to the palace of Archbishop Piccolomini in Siena, but he was soon permitted to return to his own villa, Il Gioiello, near Florence. While under house arrest, Galileo's movements were severely restricted, and he was forbidden from publishing new work on heliocentrism. Despite these limitations, Galileo found ways to continue his research. One of Galileo's primary concerns during his later years was his declining health. By the time of his trial, he was already suffering from arthritis, and in the years that followed, his vision began to deteriorate. By 1638, Galileo had become completely blind, a devastating condition for a man who had spent so much of his life observing the world around him. Yet, even in blindness, Galileo's intellectual curiosity remained undiminished. He continued to correspond with other scientists across Europe, and he relied on assistants and students to carry out his experiments and record his findings. During this period, Galileo focused much of his attention on mechanics and the laws of motion, a subject he had explored earlier in his career. In 1638, he published his final major work, Discourses and Mathematical Demonstrations Relating to Two New Sciences, commonly referred to as Two New Sciences. In this book, Galileo revisited his earlier experiments on motion, particularly his studies of falling bodies, inertia, and the strength of materials. Two New Sciences was a culmination of Galileo's life's work in physics, and it laid the foundation for much of modern mechanics. In it, Galileo described the principles of uniformly accelerated motion, the concept of inertia, and the parabolic motion of projectiles, discoveries that would later be formalized by Isaac Newton in his Philosophia Naturalis Principia Mathematica. Galileo's work in this book bridged the gap between the ancient physics of Aristotle and the modern physics of Newton, making it one of the most influential scientific texts of the 17th century. Despite his blindness and house arrest, Galileo's mind remained sharp, and Two New Sciences was widely regarded as a masterpiece. Smuggled out of Italy to avoid censorship, the book was published in Leiden, a city in the Dutch Republic, which had become a center for the free exchange of ideas. It quickly circulated among scholars across Europe, further cementing Galileo's reputation as one of the most brilliant minds of his time. Galileo's legacy in astronomy and physics. Galileo's contributions to science extended far beyond the specifics of his discoveries. His work in astronomy and physics laid the groundwork for the scientific revolution, a period of profound change in the way humanity understood the natural world. More than anyone else of his era, Galileo embodied the principles of observation, experimentation, and evidence-based reasoning that are now fundamental to scientific inquiry. In astronomy, Galileo's use of the telescope opened up a new era of exploration. His observations of the Moon, Jupiter's moons, the phases of Venus, and the countless stars in the Milky Way shattered the Aristotelian view of the cosmos and provided concrete evidence for the heliocentric model proposed by Copernicus. Though Galileo was not the first to suggest that the Earth orbited the Sun, he was the first to provide observational proof, and his discoveries forever changed humanity's understanding of its place in the universe. His work in physics was equally transformative. Galileo's studies of motion, acceleration, and inertia challenged the long-standing beliefs of Aristotle and introduced a new, mathematically precise way of understanding the physical world. His experiments with inclined planes and pendulums laid the foundation for classical mechanics, and his principle of inertia would later become one of the central tenets of Newtonian physics. Beyond the specific discoveries he made, Galileo's lasting legacy is in the method he championed. He was one of the first to insist that scientific theories should be based on empirical evidence rather than philosophical speculation. For Galileo, the truth about nature could only be discovered through careful observation and experimentation, a radical departure from the abstract reasoning that had dominated science for centuries. This approach, now known as the scientific method, remains the foundation of modern science. Galileo also played a key role in the separation of science from theology. His conflict with the Catholic Church over the heliocentric model was not merely a personal struggle, it was part of a larger shift in the intellectual landscape of Europe. By insisting that the study of the natural world should be based on observation and reason rather than religious doctrine, Galileo helped to establish science as a discipline independent from theology. This separation allowed science to flourish in the centuries that followed, free from the constraints of religious orthodoxy. Death and posthumous recognition. Galileo died on January 8, 1642, at the age of 77, still under house arrest. Though his final years had been marked by isolation and physical suffering, his contributions to science continued to resonate across Europe. His students, including Evangelista Torricelli and Vincenzo Viviani, carried on his work, ensuring that his ideas would not be forgotten. Galileo's death did not bring an immediate change in his fortunes with the Catholic Church. For decades after his passing, his works remained banned, and his name was associated with heresy. However, as the scientific revolution gained momentum, it became increasingly clear that Galileo's discoveries were correct. His ideas were vindicated, and over time, his reputation was restored. In 1758, more than a century after his death, the Catholic Church lifted its ban on books advocating heliocentrism. By 1835, Galileo's works were finally removed from the index of forbidden books. The Church's eventual acceptance of heliocentrism and acknowledgement of Galileo's contributions to science marked a turning point in the relationship between science and religion. In 1992, more than 350 years after his trial, Pope John Paul II formally acknowledged the Church's error in condemning Galileo. In a speech delivered by the Pontifical Academy of Sciences, the Pope recognized Galileo's contributions to science and expressed regret for the way he had been treated by the Church. This gesture of reconciliation was a long overdue acknowledgement of Galileo's genius and his role in shaping modern science. Galileo's place in history. Today, Galileo Galilei is remembered as one of the most important figures in the history of science. His work in astronomy, physics, and the scientific method transformed our understanding of the natural world, and his legacy continues to inspire scientists, researchers, and thinkers across the globe. Galileo's contributions to astronomy revolutionized our view of the cosmos, showing that the universe was far more complex and dynamic than previously thought. His use of the telescope opened up new frontiers of exploration, and his support for the heliocentric model paved the way for future astronomers, including Johannes Kepler and Isaac Newton, to expand upon his discoveries. In physics, Galileo's studies of motion, inertia, and acceleration laid the groundwork for classical mechanics, providing the foundation upon which Newton would later build his laws of motion and universal gravitation. Galileo's insistence on observation and experimentation as the basis for scientific knowledge remains a cornerstone of the scientific method, which continues to guide scientific inquiry to this day. But perhaps Galileo's greatest legacy is his unwavering commitment to the pursuit of truth. In the face of opposition from powerful institutions, Galileo stood by his discoveries, confident that evidence and reason would ultimately prevail. His courage in challenging established beliefs and his dedication to understanding the natural world have made him a symbol of scientific inquiry and intellectual freedom. Galileo's story is not just one of scientific discovery. It is a story of perseverance, curiosity, and the enduring human desire to seek knowledge. His life and work remind us that the pursuit of truth is often difficult, but it is a journey worth undertaking. Today, when we look up at the night sky and see the same stars, planets, and moons that Galileo observed centuries ago, we are reminded of the vastness of the universe and the limitless possibilities of human exploration. Galileo's enduring legacy. As the story of Galileo Galilei comes to a close, we are left with the profound impact of his life and work. Born into a world where the Earth was believed to be the center of the universe, Galileo's observations and discoveries revealed a cosmos far more vast and intricate than anyone had imagined. His refusal to accept long-standing beliefs without question, his reliance on observation and experimentation, and his groundbreaking use of mathematics to describe the laws of nature transformed our understanding of the universe forever. Galileo's journey from curious observer to one of history's most celebrated scientists was not without its struggles. His ideas were revolutionary, but they were also controversial. Faced with opposition from powerful institutions like the Catholic Church, Galileo remained steadfast in his pursuit of truth. Even when forced to recant his beliefs under the threat of punishment, he continued to explore, experiment, and write, knowing that the evidence he had gathered would outlast his own lifetime. More than 400 years later, Galileo's legacy endures. His work in astronomy and physics laid the foundation for the scientific revolution, inspiring future generations of thinkers, including Johannes Kepler, Isaac Newton, and Albert Einstein. His insistence on the use of empirical evidence and experimentation to test theories became the cornerstone of the scientific method, a method that continues to guide scientific inquiry today. But Galileo's contributions extend beyond the specific discoveries he made. He showed the world that knowledge and understanding are not static, that they evolve as we explore and question the world around us. He encouraged us to look beyond the familiar, to embrace curiosity and wonder, and to challenge the status quo in the pursuit of greater truths. As we look up at the stars today, we see the same celestial objects that Galileo observed through his telescope centuries ago. The Moon, with its craters and mountains, Jupiter, with its 4 largest moons, and Venus, moving through its phases. Thanks to Galileo's courage and curiosity, we know that these objects, once believed to orbit around Earth, follow their own paths in a universe far more expansive than humanity once dreamed. Galileo's life reminds us that the pursuit of knowledge is not always easy, but it is a journey worth taking. His story is a testament to the power of human inquiry and the boundless potential of the human mind. As we continue to explore the cosmos and uncover new mysteries, we carry with us the spirit of Galileo, a man whose curiosity and determination opened the door to a universe of endless possibilities. Galileo once said, "I do not feel obliged to believe that the same God who has endowed us with sense, reason, and intellect has intended us to forgo their use." His words echo through the centuries, reminding us to use the tools of reason, observation, and curiosity to better understand the world around us. And so, as we reflect on the life of Galileo Galilei, we remember him not only as the father of modern science, but as a symbol of humanity's unending quest to seek out the wonders of the universe.